Hi everybody, welcome to another video in Business Calculus, section 10.6, related rates. Related rate problems. In implicit differentiation, we differentiate the equation with two variables, x and y, and we assume that one variable is a function of the other. So when we have equation of x and y, let's just say it something like this, and we assume y is a function of x. That is in the implicit differentiation, the type problem we did on the previous section. So in this case, y is called the dependent variable and x is independent. Every time we choose x, the y depends on that x because y is a function of x. So in that case, once again, y is the dependent variable and x is independent variable. Right, so that is a problem in implicit differentiation. Now in related rates, we have at least two dependent variable that depends on one independent variable, usually time, so we use t. So we have at least two dependent variable that depends on t, pretty much. So the reason we have to have at least two because remember this is of t, so if we take derivative with respect to t, derivative with respect to time usually is a rate. So we have two variables, take two derivative with respect to t, and we have two different rates, and the rates are related into one equation. Therefore we call the problem related rates. Once again, there are two variables, take derivative of those variables with respect to t, we have two rates, at least two rates, and then because that comes from the equation, so the rates are related, so we call related rates. Alright, now so differentiate with respect to the independent variable and still use the chain rule, we obtain the rate of change of the dependent variables, and they are related, therefore related rates. So suppose we have x squared plus y squared equal to 5, the equation like we have there, but this time just by the look at the problem, we say we will find dy over dt, and the dx over dt derivative with respect to t is given, and we have x is equal to 3 and y equal to 3. So there are two derivatives of x and y with respect to t. So from here we say assume x and y are function of t and we differentiate with respect to t, kind of like what we did on the previous section. So assume x and y are function of t, and then we differentiate with respect to t. Right. How do we do that? Well, remember just like last time, if it is the function with respect to, if we take derivative of y with respect to x, and when there's y, we have to attach the dy over dx or y prime. Now similarly, derivative of x squared is 2x, but now since x is a function of t, we need to attach the dx over dt. And then same thing, derivative of 2y squared is 2y, but y is a function of t, so we need dy over dt. The derivative of 5, which is a constant, will be 0, right? So simple enough. And then at this stage, just substitute everything we know. X is equal to 3, dx over dt is 2, y is 4, dy over dt We don't know that, but it's fine. We're looking for it. Equal to 0. Right, notice that multiply, then add 2 times 4 times. Right, now 2 times 3 times 2, that's 12. Plus 8. And then we just say dy over dt equal to 0. Now we just solve for dy over dt easily. Subtract 12 and divide by 8. Step 8 dy over dt equal to negative 12. And then divide by 8 on both sides. Cancel out. And we have negative 3 over 2. Right. Yeah. Right, of course, we do that. Or if we don't want to write all of this, and technically we write in just use math notation, we can just go ahead and do this. We can just take derivative with respect to t on both sides. We just do that. Right. So, and then derivative of x squared is 2x. And now since it is derivative with respect to t, we have to have dx over dt. The variable is x, so we have that. And then y squared 2y. And then do dy over dt. And then derivative of a constant is 0. Of course, that's exactly what we have here. I just want to bring this compare this to the problem with implicit differentiation, where one variable is the function of the other. I write the same thing. But if we assume y is a function of x, we just take derivative with respect to x on both sides. So derivative of x squared is 2x. If we want to, we can still write d over dx of x. And then plus 2y. Now y is a function of x, so we have to have dy over dx. Derivative of constant 0. So implicit differentiation, dx over dx is 1. So we just have 2x. So on the previous section, we can just write like this if we want to. But now, both x and y are function of t, so differentiate with respect to t, and that's what we have, right? Again, we have this equation called the related rates. We have a rate here, a rate here, and they're related in an equation. So related rates. Right. Next, suppose x and y are function of t, so that's one given. Find dy over dt, and then we have that, right? So we don't need to write that because x and y are function of t already. We just go ahead and differentiate with respect to t. Right. Now, x squared, x is a function of t, so x squared will have t in it. X squared is a function of t as well. Y is also a function of t. So we have a function of t times a function of t. That's the product rule. Derivative of e to x, that's easy. That should be easy, right? But first, we have a product rule here. Once again, we have a function of t times a function of t. So product rule, u equal to x squared, v equal to y. So u prime is equal to 2x dx over dt, and then v prime derivative of y is just 1, and then dy over dt. Yeah, because the variable is t, we have to do that, which is the chain rule, and then the product rule. U prime v plus uv prime. Right, so put everything we have. First, the product rule, u prime v, so 2x, still just dx over dt, so u prime v plus u v prime v prime. Right, derivative of e to the x is still e to the x. However, x is a function of t, so we have dx over dt, and derivative of 2y cubed will be 6y squared, but once again y is a function of t. Right, let's just multiply them out, remove the bracket, simplify things a little. That will be 2xy dx over dt plus y squared, plus x squared dy over dt plus e to the x dx over dt and then 6y squared dy over dt. Right, so in this problem we solve for dy over dt, which is this one and this one. So for that we have to move all of the dy over dt on one side, so I think I'm just going to move this to the other side, and the dx and dx here will be easy. Right, so if we want to, we can factor out the dx over dt. Right, so first let's just factor out dx over dt, and with that we have 2xy plus x squared, x squared doesn't have, okay, not x squared, e to the x. Yeah, factor out the dx over dt. Right, this we will subtract to the other side. Then plus 6y squared dy over dt. So we have this, I write dx over dt on the back. And we can factor out the dy over dt. Again, just put that on the back. Then dy over dt. So for dy over dt, we just divide this to the other side and we are done. So in that case, we can say this divided by that. And then we multiply by dx over dt equal dy over dt. Yeah, so we solve for dy over dt. Right, so it's not that bad. If we have the equation, take the derivative with respect to t, and we have the related rates. We might just solve for it, or if we have the numbers, we can actually solve for it numerically. Right, here's an application problem where the balloon is rising vertically at the rate 5 meters per second. An observer is standing on the ground 300 meters from the point where the balloon was released. At what rate is the distance between the observer and the balloon changing when the balloon is 400 meters height? Right, so we just have to draw, see what we have. So the balloon is rising and observer stand 300 meters away from where the point where the balloon was released. Right, so we just have, we stand here and the balloon is about say 300 meters away, and the balloon is released to the air. Just draw the balloon. Assuming that there's no wind, so the balloon just goes straight up. From where it is released. Right, and at that instant it is 400 meters above the ground, 400 meters high. And the question is, at what rate the distance between the observer and the balloon is changing when the balloon is 400 meters height? So the question gives us that. So this is the distance between the observer and the balloon, and the question asks for what rate. So that is with respect to t, of the distance with respect to t. By the way, if the distance we use d, then we have d, that doesn't sounds not right. So we use something else. Let's say the distance is r between the observer and the balloon, and the height of the balloon is, let's say, h. I said we assume that there's no wind, so the balloon just goes straight up the air. And so that we'll have the perpendicular angle, and assume the ground is perfectly flat. I mean the ground is perfectly horizontal. So in that case we have r square equal to h square plus 300 square. That's the Pythagorean theorem. So in the right triangle, the hypotenuse square is equal to the sum of the square of the legs of the right triangle. Right, so like that. Right, so let's see what is given. The weather balloon is rising at the rate. So every time we see rate, that is derivative with respect to t, and this is 5 meters per second, and the balloon is rising, so this is dh over dt is 5 meters per second. And it's at what rate? So the distance between the observer and the balloon. So distance between the observer and balloon, and what the rate of change of that. So the question is dr over dt is what? And then we just have these scenarios here, right? So from here we say assume r and h are function of t and differentiate with respect to t. So those are pretty standard. So I'll say assume r and h are function of t and now we just differentiate with respect to t. So we derivative r squared is 2r, and we have dr over dt equal to h will be 2h, and then dh over dt 300 square, that constant equal to 0. Right, so related rate. So let's say we have what we have the height at that moment is 400, so we know h is equal to 400. We know the h over dt is 5. meter per second. Let's just use the number. Right, so we have h, we have dh over dt. We looking for dr over dt, so we still need to know r, right? Luckily we still can use that equation, r square equal to h square plus 300 square, right? So h is 400. Just put it here. Right, so just like 3 square plus 4 square is 5 square, this is 500 square. Right, of course. And we can take square root of that. Just copy and paste there. So r square is 500. So take the square root on both sides. There's plus or minus. So that plus or minus 500. However, the distance between the 2 points cannot be negative. So it's just 500. So we have h is that, and then r is 500. Now we just substitute everything in the equation. 2r 500. dr over dt, we don't know that, but we solve for it. And 2h 400. dh over dt is 5. So dr over dt, just divide by 2 times 500 is 1,000. Just divide by 1,000 on both sides. And this 400 times 5, 2,000, and that's 4,000 over 1,000. So just 4. Right. Right. So that's the number. However, what will be the unit? So first, if we look at r, the unit for r is the distance between them. So the distance will be meter. So the unit for dr is going to be meter, and dt, that will be time. So meter per second. Right. So if we actually want to put everything in, we can also write 2 times 500 meter, because that what r is, meter, and then dr over dt equal to 2 times 400 meter, and then 5 meter per second. Right. So we can just cancel out the meter on both sides, and then all the numbers work out. At the end we still have meter per second. Right. So usually we can put all the unit in like that, or we just put the numbers. At the end we determine the unit. Right, so this is a typical related rate problem. Sketch the graph and then identify the variables. So they identify the variable and see how they related, and then find derivative with respect to t. That usually that's the chain rule, and then we're looking for solve for the rate that we don't know. Oh, simple enough. Now let's look at this problem. A rock is thrown into a steel pond, cause a circular ripple. If the radius of the ripple is increasing at 2 feet per second, how fast is the area changing when the radius is 10 feet? So I'm trying to draw in 3 dimensions here. If you drop a rock into a still point will cause the circular ripple. Okay, so that is a perfect circle, but that in 3D shows like that. So the rock cause the ripple. Right. If the radius of the ripple is increasing, so we just underline what we have. So the radius is increasing at 2 feet per second, right? How fast is the area changing? How fast that a rate of the area? So if we say the area is A, so we're going to have the dA over dt. How fast the area changing? We don't know that. When the radius is 10 feet. I should have 10, the radius is 10 feet and the rate of change of the radius is 2 feet per second. So we can say dr over dt is 2 feet per second. Right, and then we have A and R. So what is the formula that relate the radius and the area? And that is the area per circle. So the area per circle, pi r square. Then we check the derivative with respect to t. Before that we say assume A and R are function of t. And then we differentiate with respect to t. Right, so derivative of A is just 1, and then just dA over dt. That's what we're looking for. Equal to pi r squared. Pi is a constant, right? So just say pi times 2r, and then dr over dt. Well, we have everything. We just substitute it. This time we solve for dA over dt. We substitute everything with units. Just 2 pi r dr over dt. Now we evaluate at r equal to 10 feet and at dr over dt (2 feet per second). I substitute that. Sorry, r is 10 feet. Dr over dt 2 feet per second. Right, now we have feet times feet will be square feet over second, which is would make perfect sense because the area, the unit of the area would be the square feet. It's perfect. And then derivative, the unit for t is second in this case, so we have square feet per second. Perfectly fine. Now combine all the numbers. 2 times 2 is 4 times 10, 40 pi. To just say 40 pi. And then square feet per second. If we want an estimate, 40 pi is 125.66. Square feet per second. Right. Now, I suppose that now we go to the next one. I suppose that for company manufacturing transistor radios, the cost is given by that and the revenue is that, where the production output is X radio for 1 week. So this is important, we need that. And the production is increasing. So what is the production? Okay, production is X radio, so X is production, and the production is increasing, so that is the rate of production. So we have the X over dt is 500. Production is increasing at the rate of 500 radio per week, so the X over dt is 500, and we can say radios per week. And when the production is 200 radios, so when X equal to 2000 radios, and the cost is that and the revenue is that. So we have just want to write, we this case we say assume everything is function of t and then differentiate with respect to t. So the cost function c equal to 500, 5000 plus 2x, and differentiate with respect to t. We have dc over dt. Derivative of 500 is 0, derivative of 2x is 2, and then we have dx over dt. And then just substitute in here, dx over dt is 500 radios per week. Right. The question is find the rate in increasing of the cost. The cost function is that. So the question at first, find the rate in increasing in the cost, which is dc over dt. So that's the question. So we're looking for that. And then dx over dt is 500 radios. I'm not going to put unit here because if we put unit it might not work out. Because if that is radios per week, this doesn't make sense. The C is cost, should be in terms of money, maybe dollars, hundreds of dollars, something like that. So we just have 2 times 500, so that's 1000. That's simple, right? So that is the cost, the rate in increasing in cost is given by that. Next, find the rate in increasing of the revenue, right? The revenue is 10x minus 0.001 x squared, and once again differentiate with respect to t. We have dr over dt, and that's what we're looking for. And then 10x, derivative of 10x is 10, and then once again we need dx over dt, and then minus 2 times that, 0.002 x dx over dt. At this value, substitute that in, and again we will leave the unit out because this should be some term of dollars over a week. Dx over dt, that's 500 minus 0.002 x at 2000, and dx over dt is 500. Right, so we have that. So that is 5000 minus 0.002 times 2000 times 500. We have 3000. course, think about this, the cost and the revenue. Of course, if we want to produce more, that's going to cost more money. And if we want to, of course, when we produce, assume that all of the radios that we produce being sold. So in that case, of course, the revenue should increase as well. And then find the rate in increasing in the profit. So the question here is asking for dP over dt. Right. Of course, we can say the profit is equal to the revenue minus the cost, and then we can substitute the function and simplify. However, if we just differentiate with respect to t, we just have dP over dt equal dr over dt minus dc over dt. Right? Doesn't matter what the revenue and the cost function are, that's what we have. And then we just substitute in what we have. First 1,000 for dc over dt and 3,000 for dr over dt. So we have 3,000 minus 1,000, and that gives us 2,000. And this could be in terms of some dollars per week. Could be $1,000, I mean $2,000, or if this could be in terms of thousand or hundreds of dollars, who knows? But in case numbers, that's what we have, right? So of course, we have the function. In this case, it's simple. We just take the derivative with respect to t, and the question asks for dc over dt, dr over dt, and then dp over dt. Right, and with that we finish section 10.6. As always, thank you for watching, and see you in another video in business calculus.